Hello everybody, I'm here with a problem where I'm trying to actually show you how we can describe velocity and acceleration in normal tangential coordinate system. In fact, I want to show you how you can determine the normal and tangential component of acceleration actually, and how we can derive those outcomes actually. So let me start by saying that if you have a particle that travels from point 1 to point 2, a short time and a short distance ds, very short distance ds. So if we define the tangential axis at position 1, so that would be the t1 axis here. Remember, tangential axis is always tangent to the path. And then perpendicular to that would be n1 axis corresponding to that position. And then look what happens. As the particle travels to position 2, you'll see that actually the tangential axis change direction. So NT coordinate system is what we call a local coordinate system. You see the direction changed. Local means the axes are only good for that location. This is unlike X and Y axis, rectangular system, where X is always horizontal and Y is always vertical. Okay? So if you draw the normal axes, N1 and N2, they're going to intersect at point C, where point C is known as center of curvature. And then the radius of this path, remember this is a very short distance, so the row here and the row here, the radius are going to be the same, and that's called the radius of curvature. All right, so my objective here is to show you how we can define velocity, and then after that we can go ahead and come up with the components of acceleration, normal and tangential components. So I started by saying, okay, we know from the simple geometry that ds is, meaning this arc length, is equal to radius, which is rho, times this angle, d theta. So ds equal rho d theta. I'm going to start with that equation, and then I'm going to divide by dt, and I've shown you here. So ds over dt becomes rho d theta over dt, and d theta over dt obviously is theta dot. So velocity becomes rho theta dot. So yes, the magnitude of velocity could be described as rho theta dot, but we, rarely ever use that form of the equation to determine velocity. Of course, this equation is used in a minute when I want to find the component of acceleration, and in particular the normal component. So now, let me describe velocity vectorially to you. What would be velocity of this particle? Well, we know that velocity has some magnitude, which we call it v. Yes, the magnitude is rho theta dot. But velocity, by definition, has to be always tangent to the path, which means it's always along the tangential unit vector. So you see this u sub t, by the way, here, that I've shown in green, is the tangential unit vector, meaning it's the unit vector along the tangential axis. What is a unit vector? Unit vector has a magnitude of 1. Just like the unit vector along the x-axis, horizontal axis is I. I has a magnitude of 1. Or j is the unit vector along the y-axis. So here, the unit vector along the t-axis is denoted by u sub t. Okay? It has a magnitude of 1. All right, so if that's the velocity, and remember, velocity doesn't have any normal component. So because velocity cannot have any normal component because it's always tangent to the path. So I just wanted to show you that, right? But let me erase this actually. I don't want to confuse you. So we start with velocity equal, as a vector equal v times u sub t. So how about acceleration? Let's go ahead and try to find acceleration. Acceleration is the derivative of velocity. So if we go ahead and take the derivative of velocity, which is v u sub t, be careful guys, we have to use product rule. So we take the derivative of velocity with respect to the derivative of the first times the second plus first times the derivative of second. So dv dt times the second, which is just u sub t, plus first, which is v, times the derivative of the second term, which is actually the tangential unit vector. So the question now is, what is the derivative of the tangential unit vector? That's what I want to show you. That's what so different between this coordinate system and the xy coordinate system. So let me show you how we can determine du the derivative of the tangential unit vector with respect to time. So the way this is done is basically keep track of these unit vectors. You see at position 1, the u sub t is like that. Let me kind of enlarge it for you so you can see it better. So this is u sub t at position 1. And then I'm going to draw u sub t at position 2 right here. So you see this would be this guy. You see direction change. What is this angle here between these two unit vectors? Obviously it must be the same as d theta, because the angle between the two perpendicular to these tangential axes is also d theta here, right? So let me call this guy the change, because this is, by the way, the change in these two, the difference between this and this one, right? Like you have two vectors a and b. This vector here would be c, which c would be, b minus a. So what I'm going to do now, I'm going to say, okay, look, what would be this, the length of this change? The length of this change, just the length itself, okay, the length of the change is equal to the length of this vector, this u sub t, or this one, doesn't matter, times the angle. Just the same thing as I did here. I said ds equal rho d theta, right? But what is the length of a unit vector? The length of a unit vector, by the way, absolute value here means length. What is the length of a unit vector? Is 1. So this actually becomes d theta. And then now if I divide by time, right, what happens? Then I have d theta over dt, so that becomes theta dot. So far we've determined that the rate of change of u sub t, not as a vector though, is just theta dot. But now let's give it a identity. What about the direction of this change? So now I put the hat on, right? So the question is, as this guy approaches this guy, right, what would be the direction of this change? The direction of this change must be 90 degrees to this, which makes it along the normal unit vector. So actually I can just put it right here for you. So the direction of this guy would be normal unit vector. So that's the derivative of the tangential unit vector. So now I can replace this guy by what? Theta dot u sub n. So let me move to the next page and finish this up for you, and then I'll just make some general observation of the two components. So let me rewrite the acceleration. So remember, acceleration, let me go back actually to black here. So acceleration was dv dt, right, u sub t plus v du t with respect to time derivative of this guy. And this guy became what? This guy became theta dot u sub n. So if I rewrite this for you now, a becomes what? dv dt u sub t plus v theta dot u sub n. Now, a minute ago in the previous page, you guys remember here I said velocity is what? Rho theta dot, right? Let me bring that here. Why don't we replace theta dot by v over rho, right? If I replace this guy by v over rho, let's see what happens. Acceleration becomes dv dt u sub t, right? Plus v squared over rho u sub n. So this is the acceleration described vectorially. And let's try to make sense out of this equation. What does this equation mean? This equation implies that this dv dt, which is attached to the tangential unit vector, must be the tangential component of acceleration, dv dt, or v dot, or simply rate of change of speed. So you see, what is definition of the tangential acceleration? Is rate of change of speed. And this guy, which is attached to the normal unit vector, must be a sub n. A sub n is v squared over rho. You see, this component, this normal component of acceleration, is as a result of what? As a result of change in direction of a speed. Change in direction. Because you see, when you go along a curved path, what happens? So when you go along a curved path, if the speed here is like that, yeah, the magnitude could change or it could be constant, but definitely the velocity changing direction. Okay, so that's why you have what we call centripetal acceleration. So this is known as centripetal acceleration. All right. So basically, in general, there are two components of acceleration. So if this is the tangential axis, let's say, at a given instant, and this is the normal axis, we have a tangential component, which is this guy, dv dt, rate of change of speed, and there is a normal component, which is known as centripetal acceleration, and is v squared over rho, and then the total acceleration or the magnitude of acceleration is the resultant of the two, would be this guy. So A, as you've seen in other videos, would be A sub t squared plus A sub n squared. This would be the magnitude of acceleration. Okay, so you've seen these components before, but I just wanted to show you how these equations, where actually, where did the v squared over rho come from? So, and you could see here how it is derived. Okay, thanks for watching and listening.